Welcome back, guys. So we're doing chapter 8 today. I'm going to start at the beginning and get up until effect size and power, which the next video already covers. So let's go ahead and get started on, let me pull it up, chapter 8, which is hypothesis testing. Okay, so for hypothesis testing, we went over this in class, but I'm going over it again so that we can kind of just have it here and concise with everything together. We talked about the average height of the adult woman being 5'4", and the question was, are basketball players, especially female basketball players, at UTampa, why not? Because we can actually grab the data. Are they significantly taller than the average woman? And so this was the question where we want to compare two different things. We have a population average, and we want to compare an average that we get from a sample, the sample being the UTampa female basketball team. Okay, so the textbook gives an example from University of Connecticut, but I figured why not? We can actually grab the data from local, all the individuals that we have on our basketball team here. We can go and calculate their average. I actually went ahead and calculated standard deviation as well. And so what we can see for 5'4", this would be 64 inches. But for our example here at UT, it's going to be 69 inches. And so the question is 69 significantly larger than 64? In order to answer that question, you need to take the standard deviation into account. And what we're going to do is we're going to take the standard error into account. We need to first calculate the standard error. If you guys remember, after that, we need to calculate the z-score. Then we're going to see where the z-score falls in terms of the critical region. So let's jump into that. So the logic of hypothesis testing is that you first need to start with stating a hypothesis about a population, not your sample, about the population. So usually this is some type of population parameter, like an average. Next, we want to figure out what do we expect from the sample that we collect. So do we have an estimate for how the sample statistic will change? And this is important because if nothing's going to change, then why are we doing hypothesis testing? I mean, you could expect that nothing is going to change. But more likely than not, we think that some change will occur. We'll talk about directional hypotheses later on, where you say, I think it's going to get bigger, or I think it's going to get smaller. But typically the safer route and the best practice is that we actually go with some change will happen, not necessarily which direction it will go. Then you actually have to do data collection. You have to collect your sample. You get a certain amount of people, right? For you guys, you're going to be collecting 4 individuals. So your N is going to be 4 here. And you're going to take measurements related to your research question. And these could be one-time recordings. It can be before or after the recording. It can be questionnaire data. It can be heart rate data. It can be anything. Okay, but you collect your sample. You collect your data. And then you compare your data with a prediction that you made in your hypothesis and what you expect. So there's 2 options here. Option 1 is that your sample statistic is consistent with your prediction. So your hypothesis is reasonable. Some change actually occurred. Yes, female basketball players are taller than the average woman. Or option 2, there's a large discrepancy between the data and your prediction, right? So I predicted that female basketball players are going to be larger. What I measured was completely different. Maybe my hypothesis is incorrect. So hypothesis down here. Hypothesis is probably wrong, and I need a different hypothesis. This is when we are seeing what shift. Here we have the term treatment, and right, treatment can really be all-encompassing in terms of, yes, it could be therapy treatment, and yes, it can be medication treatment, but it can be really anything that you do to your sample. So if you're doing some type of behavioral intervention, or a somatic intervention where you're giving medications or giving hormones or something like that, you expect some change to happen. And that change should affect the average, but really we don't really expect it to affect the variability necessarily. So standard deviation is not affected, but we already went through what happens when you add or subtract values, a constant to each x, each score. How does that affect the average? It simply will increase or decrease the average by that constant. So it creates a shift in the distribution. I hope my voice can withstand going through this whole thing. It almost disappeared, but I think I have it mostly back by now. Okay, So when we're doing research, we have the research question about our population, but what we're actually doing the research on is the sample that we collect. And the thing is, we don't usually know what the treated population would look like because we can't do it on the entire population. So this is why we collect a sample and we do our treatment on the sample, and then we make an inference back onto what this has to say about the population. So hypothesis testing is done on the treated sample, and if I added a little arrow here coming back to the unknown treated population, the idea is what kind of inference can I make? If in future I do this research on a new sample, is it going to have the same outcome? Is it going to be reliable? And so if I were to treat the entire population, can I have a pretty safe bet that I know what's going to happen to the treated population? Okay, so let's come back to these 4 steps of the hypothesis testing. The first is stating the hypothesis, and in fact what we're really doing is stating 2 opposing hypotheses. The first is the null hypothesis. This one states that no change happens, or that there is no difference. So for example, no, female basketball players are not significantly taller than the average woman. So the null hypothesis states there is no change or there is no difference. So whatever my treatment was, my IV, my independent variable, the thing that I manipulated, for the null hypothesis, I would expect no change to happen. In your textbook, they use the example of tipping. If female waitresses wore red shirts, would male customers tip more? And so we start with the average tipping without any kind of manipulation of 16%. So here the null hypothesis states that it will stay at 16% and it's not going to change. The alternative hypothesis, this is your actual real hypothesis. This is, or also called the scientific hypothesis. This is the one that we actually think is some changes truly happening here. So it's the opposite. It's that the treatment will have an effect, that there is a difference. We don't necessarily say in what direction it goes, just that it will be different. So stated down here, H1, our alternative hypothesis, is that the average of tipping for wearing a red shirt is going to be different than 16. So again, this can be larger, this can be smaller. Our hypothesis really is going with it's going to be larger, but you never know what happens in the real world. We just are stating that a difference is going to happen. And it's really important that these 2 hypotheses are mutually exclusive and exhaustive. So both cannot be true at the same time. It has to only be one at a given time is true, and it has to cover all of the possible conditions that we have. So we either reject the null hypothesis. The goal is we want to reject the null hypothesis. This is the main thing that we want, because we want to say, no, a treatment actually happened, some effect happened, there is a difference. We want to safely reject the null hypothesis. Or we fail to reject it because our data says there is no difference. So then we have to actually go with the null hypothesis, there is no difference. So, and I mentioned this in class, and this is really important, we don't prove anything in science. That's left to mathematics. So we don't prove the alternative hypothesis. We either reject the null hypothesis or we fail to reject the null hypothesis. And what we do when we collect data is we basically provide evidence to support the alternative hypothesis, our prediction. So, right, our prediction is the alternative hypothesis H1, the one where we actually think a change is happening. Okay. So that's step 1, stating the hypothesis. Step 2 is we're going to set the criteria for the decision. So this basically means when do we think that a difference is, when do we think that it is large enough to say that there is a difference? So a sample mean that is near the population mean would mean no effect. Not to have 2 means in there. But it means there would be no effect. So we basically are looking for how outlier do you need to be, how extreme do you need to be to where we can say you are different enough from the population, some change actually occurred. So we need a way of determining when something is near versus very different when we look at a distribution, a sample, a distribution of sample, I don't think I'm getting the word right, but the distribution of sample means where if we are in that middle 95%, then you are no different than that null hypothesis. But if we're on the very, very edge of it, meaning we're on the extremes, then that means we are very different from the null hypothesis. It means we have more evidence to support the alternative hypothesis. So that's what I was with my hands trying to illustrate here with the distribution, right? If I am here in this 95%, I'm going with 95% because we talked about this in class already, but if I am in the majority here, in the most likely scenario, in terms of where my sampling distribution is, then realistically no change happened. But if I'm out here in the extremes, it's very likely that some change actually occurred. And so option 1, the sample mean is consistent with H null, right? The values go around the center of the distribution, so there is no difference. Or option 2, the sample mean is very different than the null hypothesis, right? Keep in mind this is according to the null hypothesis. If I'm very different than the null hypothesis, then that supports the alternative hypothesis. And the question is, where do we set that boundary along the sampling distribution? And really the answer that we came up with in class, which is the gold standard of science, is an alpha level of 5%, meaning 5% extreme individuals who are on the left or on the right and don't belong with 95% of the main distribution. So we call this the level of significance or the alpha level. Some commonly used alpha levels, as I said, the gold standard is going to be 5%, right? If you look this up in your unit normal table, it's going to be 0.05%, or not percent, 0.05, equating to 5%. Actually, no, if you look it up in the unit normal table, it's going to be 0.0005. Am I getting that right? No, I think I'm just going to trust myself how I wrote it here in the slides that it's 0.05. Whereas we can also have 1%, which is a little bit more stringent, or we can have 0.1%, which is even more strict in terms of how much we want that person to be in the extreme, how much in order to say that is significantly different. Right, so we're talking about these extreme regions. The middle probability here is most likely to be according to the null hypothesis, whereas if we're further out here, it's very unlikely that I am actually part of the null hypothesis. I am probably the alternative hypothesis, or I'm very different from them. So we call this the critical region, determined by the alpha level. And if I am in the critical region, then I have to reject the null hypothesis, and I go with the alternative hypothesis instead, which is my prediction, my scientific hypothesis. So the data provides evidence that the IV actually had an effect. So in order to do this, when we actually have problems that go into, are these two things significantly different, we're going to be using the unit normal table again, and we're going to use z-scores again. So in most cases, the distribution of sample means is normal, has a normal distribution, especially if we have more than 30 individuals, which we talked about. Knowing our boundaries will give us a precise z-score location, right? So if I'm talking about the extreme 5%, then each tail, the bottom tail and the top tail, is going to have 2.5%. If I look that up, I can look this up in the unit normal table, column C, which is the tail. If I look for this proportion, which again, I really should just trust myself that I know what I'm doing when I have this on a slide, this 0.025%, this corresponds to a z-score of 1.96, and this is that magical number, 1.96. If I want to support my hypothesis, if I want to reject the null hypothesis, I want z to be larger than 1.96, because that means I'm in the critical region. So different z-scores for each of these alpha levels, right? 1.96 for my alpha level, 5%. If it's 1%, then that z-score is going to be a little larger, 2.58. And I put plus minus here because you can be on the top or the bottom portion of that tail. Or if I'm going to be even more strict and go with 0.1%, right? 0.1%, which is very, very small, which we're talking about 99.9%, right? The extreme 0.1% out of that, my z-score is going to be 3.3. Right, so a very large z at this point. So then what do? I collect my data, and then I get my sample of 4 people, which you guys are doing. And the goal is to compare that data that I recorded, that I collected, with the null hypothesis, with that H null. In order to do this, I need to calculate the mean, right? So maybe the mean resting heart rate, or if we're looking at anxiety scores, maybe I want to look at the average anxiety scores after they did one of my tasks. And I'm going to need all that data, including down here. I hope you guys recognize this. This is the standard error down here, not the standard deviation, the standard error. I'm going to need to compute I'm going to need to compute a few things in order to get my z-score. But the point is, I want to calculate that z-score so that I know, am I in the extreme, am I in the critical region, or am I with the main sampling distribution? And so this is my z-score calculation, right? M minus mu here, sample mean, minus the hypothesized population mean. This is the H null over the standard error. And then step 4, once I calculated it, then I make a decision. Do I reject the null hypothesis? So my sample data is in fact located in the critical region, right? It is very unlikely to occur if H null is true. And by rejecting, I conclude there is evidence to support it. That's option 1. That's the option that we like. And let's just go with some fake data real quick. In terms of the tipping example, if someone with a red shirt, if a server, female server with a red shirt, is serving male customers, are the male customers going to tip more? And so the average tipping was 16%, and what we recorded in red here is 17.2%. So the question is 17.2 statistically larger, so more significantly different than 16? And we can first calculate the standard error. So we have standard deviation given to us, so we plug that in. We had 36 individuals that were recorded. We plug that in, the square root of n, and we get a standard error of 0.5. So I haven't used m yet, I'm just calculating the standard error. And then I can plug these numbers into my z-score. And the z-score is going to include my standard error that I just did, as well as the average, and I get plus 2.4. So 2.4 is larger than 1.96. So we can make the decision of rejecting the null hypothesis. To give you option 2, where I fail to reject, this means that the sample data is not in the critical region. So for example, if the tipping was 16.4%, this was a z-score of 0.8. That's not statistically large enough. We're not in the critical region. I am not different enough from the null hypothesis that I can say I can safely reject the null hypothesis, so I fail to reject. So we want to reject the null hypothesis because that means we have data to support that my alternative hypothesis is true. Okay. So summary of those 4 steps: state the null and the alternative hypothesis, select an alpha level, which goes along with step 2, locate the critical region. I'm setting the criterion for where am I going within a standard alpha level of 0.5, or am I going more strict with 1% or 0.1%. I compute the test statistic for which I need the standard error and then the z-score, and then 4th, I make a decision. I either reject or I fail to reject. And again, for what you need to do those step 3 calculations is I need the standard error. And you can write this on your formula sheet in terms of like decision process, kind of like a flow chart. Once I get to step 3, when I need to compute it, I need the formula for standard error. I need the formula for the z-score. Okay. This is just a refresher. This was our z-score when we used scores. So the z-score for a score x, right? I had x minus mu over the standard deviation. When we're talking about a sample mean, this needs to be like mega highlighted sample mean, right? M, we're not using x anymore. Then we're going to have m minus mu, so we're doing the deviation over not the standard deviation, but the standard error. We use the standard deviation to calculate the standard error. So The z-score really represents this ratio between the actual difference that I calculate, right? Basketball players are this tall, average person is this tall. That actual difference over what do I expect there to be a difference. The standard error represents expected difference between those two scores, right? And so I want z to be large. If z is large, that means what actually happened was a lot larger than what I expected. And this is just reiterating some of the stuff that I had from the central limit theorem. All samples of a population together will have the average that is exactly the population mean. It's called the expected value of m. So m is an unbiased statistic, which is really handy. If I took all samples and I took their averages, I would end up with a population average. So that's for all samples, but with a single sample, I'm going to be off. I might be off by a little, I might be off by a lot, I don't know. But the average amount that I can expect to be off is the standard error. That's my variability in how much I think I'm going to be off. So the standard error provides a measure of how much distance is expected on average between a sample mean and the population mean. Right? Sometimes it might be small, sometimes it might be big, but on average, it's going to be a certain amount. And that's my variability. The standard error is the variability of my sampling distribution. Okay, so let's do this step really quick with the data that I actually grabbed from the UTampa basketball players. I had 69.2, right? I had calculated mu, I had calculated the average, I calculated the standard deviation. There were 15 people that I had the data from. Their average was 69.2, and then I could actually right, small s is standard deviation of a sample. I could actually calculate that as well. So to figure out if UTampa female basketball players are significantly taller than the average woman, first thing I need to do is calculate the standard error. So I just simply plug in these numbers. So I plug in my standard deviation over, I had 15 people to work with. So the square root of 15 apparently is 3.87. I did not know that. And then their ratio gives you 1.55, so that's the standard error. And then I use the standard error in my z-score calculation. So again, I plug in my numbers. Now my m here is 69. So I'm getting a difference of 5.2 over the standard error, which gives me 3.35. And this should set off some big alarm bells with you guys. If I get something as big as 3.35, that should be telling you it is significant, because this is larger than 1.96. I'll put these again down here. If we're going, and we set this criterion at the beginning, I set a criterion of 5%, my z-score is 1.96, so I'm definitely above that. In fact, I'm actually, I'm even more in the stringent zone of 0.1%, so it's very statistically significant. Are the UTampa female basketball players very, very tall compared to the average woman. Okay, so that wraps up our example and hypothesis testing. Next, we need to talk about errors that happens when you're doing hypothesis testing. And my voice is still keeping up, so that's good. Okay. So when you make a decision, right, there's two types of errors that go along with these decisions. The first decision was that I reject the null hypothesis, which is good. It's the one we want. But sometimes we make a mistake where we actually rejected the null hypothesis when there was no effect. We thought we saw an effect, but there wasn't. So when we calculated it, our z-score told us, yes, you're in that extreme, but sometimes in reality there are extreme values. But that doesn't necessarily mean that it is that something changed with your manipulation. So this is actually kind of the worst error that you can make, is when you reject the null hypothesis when in fact there was no real effect. And I'll talk about the errors in a little bit more detail in a second. The second one is where we fail to reject samples not in the critical region, and this one is more of a, oh, okay, where there was an effect, but I didn't find it, right? So we failed to reject it when there really was an effect. So the effect exists, I just didn't find it. Ideally, I run the study again with more people and I'll find it in an ideal world. So this type 1 error where we rejected the null hypothesis and we thought we found evidence to support something when really there was no effect, this can lead to false reports in the literature, which is why replication is so important. We want to replicate, we want to show that these results are reliable. So replication is essential in research. This can lead to false theories, developing new experiments that are all based on a false theory because one study had a type 1 error, and now all those studies, future studies, are based on it. So the alpha level actually determines the probability of a type 1 error. So the probability of committing a type 1 error is actually the alpha level, meaning I have a 5% probability of committing a type 1 error, which doesn't seem like it's very large, but at 5% probability, you're like, but it happens, it still happens. So researchers, they can control this by setting a more stricter alpha level, such as 1%, or even more stringent with that 0.1%. That means 0.1% of the time am I going to make this error. Type 2 error, where I failed to reject the null hypothesis when there really was an effect. This is simply that the researchers didn't find the results that they hoped for. So really, the main source of error for this, or the main source for the error, is that the sample was too small. And realistically, when you guys do your studies, you're going to have the same thing. You're only going to collect from 4 people. You might not find a statistically significant difference, and that's probably because your sample size was so small, right? If you increase your sample size, then you would end up finding, you would find the effect, and you would, you'd find the effect. So realistically, you guys are going to be committing type 2 errors, not by any mistake that you're doing, but simply because your sample size was so small. So the effect was not large enough. We need to try again, but better, ideally bigger sample size. These consequences way less serious than type 1 errors, right? Type 1 errors could create a whole building of experiments that all are based on a faulty theory. But in type 2, cannot determine, the thing is we don't know the probability of committing this type 2 error, but we do assign it simply as beta, whereas type 1 error was alpha, the alpha level. Here we simply refer to it as beta. There's a lot of different factors that can contribute to why we get a type 2 error. It's not just sample size, it can be other things as well, but we simply assign that as the probability of committing a type 2 error is beta. And again, we don't know usually the exact value. So this just sums it up in a table format, if table format is what you like, right? So actual situation, there was no effect, but I rejected it, type 1 error. The effect exists, but I failed to reject, type 2 error, right? So if you want to work it out this way, to determine when you make that error in hypothesis testing. So talking about this more stringent alpha level, wrong button. Lower alpha level means less chance of committing type 1 error, which is good, right? But the thing is, that means we need more evidence for finding that effect, which again means really, really large sample size usually. So extremely low alpha is great for not committing those errors, right? A 1 in a million chance, which for something like pharmaceutical companies, we want that 1 in a million chance that you're going to have a stroke if you take this medicine, right? We want that to be very, very low. But in order to do that, then I need enormous sample sizes, right? Thousands and thousands of people, if not on the millions, so that we have a huge treatment effect in order to find that. So it's kind of a trade-off. We want to eliminate that error. If we want to eliminate error, means we need greater sample size, or we go with a smaller sample size in a more liberal alpha level. We can't go more liberal than 5%. 5% is really the kind of the cutoff. But we could go with something more like 1% to be a little bit more strict, increase our sample size, then we can be a little bit more confident that we're not committing a type 1 error. Okay, just a little bit more about the hypothesis testing. I'll be wrapping up here in a minute. So journal reporting, this is important of how this ends up looking in proper journals and how you guys are going to report and talk about it in your paper. So we might say wearing a red shirt had a significant effect on the size of tips left by male customers. We report the Z-score, and this is how we write it. This is how we write the statistically significant portion of it. I used to be able to get my arrow to turn red, but I can't do that right now. But this P less than 0.05, this is our alpha level. This is our level of significance, where we're saying P, the probability, right? My probability was less than 5%. I was safely in the critical region. So whenever something is significant with an alpha level of 0.05 or 5%, we say P less than 0.05. We don't report the exact P value, even though you could look it up. We just say less than. So for example, reporting on the example that we did with the basketball players, the women's basketball team at the University of Tampa are significantly taller than the average woman in the population. Notice how I use the word significant here. Only if it's statistically significant can I use that word. Again, I report the Z, and in this case, the alpha level was actually 0.1%, so 0.001. Right, if you're having, you just have to do the whole transferring like times 100 to move the thing over by two spots. If we want to report it in terms of figures, we want to show graphs, we can use asterisks to indicate that. So one asterisk is an alpha level of 5%, 2 asterisks is 1%, and then 3 asterisks indicate asterisks. When you say a word and it just starts sounding weird. 0.1%. Right, so significant means that the null hypothesis was rejected. This is what we want. If we don't want to commit a type 1 error, then we go with a more strict alpha level, like 1%. Okay, this is just taken from one of my papers where we might do that reporting, and when we talk about the results, we're not there yet, but when we do the results section, this will be really relevant to you guys. But you can see here is a P level of less than 0.01, another P level, and down here a P level less than 0.01. Oh, I had it highlighted. I didn't have to do that with my mouse. Down here though, for example, do I have it highlighted? Yes, I do. For example, one of these was not significant. Don't worry right now about F and T. We haven't learned about that yet. We'll learn about T in this class. Instead of Z scores, we're going to start doing T scores. And then when you go on to Stats 2, you'll do F values. But you can see here, when it's not significant, we report the exact P value. So here, this Pillai's trace for the overall multivariate test was not significant. We report what that test statistic was, right? In our case, it's going to be Z scores. In this case, it's an F value. And then we say P is 0.10%, so it was not significant. You can see down here, actually, there's another one. P equals 0.46%. That was also not significant. When we show it in a graph, as I mentioned, you can use asterisks and indicate the difference between two things is significant, whereas this one, for example, was very significant. So you can use it in different ways. And later you guys are going to learn about R squared in Stats 2, and there we also use our asterisks to indicate how significant it was. Okay, to really demonstrate this idea, and I think later on I'll have actual numbers plugged into this to really illustrate this, but how the standard error affects the size of the Z-score. The standard error goes in the denominator here on the bottom, right? And then up here we have our deviation score as we usually do. So if I have a standard error, formula for my standard error, inside of the standard error is the size of my sample and its denominator. Whereas in the top I have variability of the sample, which is my standard deviation, right? So if I want, generally what I want is a large Z-score, because I want it to be statistically significant. So I want a large Z-score. I want there to be a big difference between what my sample, what I record, and what the population ends up being, or the null hypothesis. And I want a small standard error. This is what I want. Because if I have a small standard error and a big deviation, I'm going to get a big z-score. In order to accomplish that, to get that small standard error, I need a small standard deviation, so not a lot of variability, and I want a very large sample. These are the two parameters that are going to contribute to, in the end, having a large z-score. I want a large sample, and I want small variability. Okay? Keep these in mind. These are the kind of questions that on the exam come up in terms of how does variability affect the z-score, or how does sample size affect the z-score, or how does sample size affect the significance of your study, right? This slide is demonstrating that relationship between those things. And to visually demonstrate that, we want low variability down here because we want good separation of those two probabilities, of those two curves. And the top one here, I have high variability and they're overlapping. With that overlap, I don't have a lot of confidence to say that those are significantly different from one another. Whereas on the bottom one, there's nice separation. I can clearly see difference between those two distributions. So I can safely say the basketball players are taller than the average woman, or tipping was significantly larger than it would be for just 16% tipping, right? So variability significantly affects the z-score, which affects statistical significance. Oh, I had the calculation in here. Okay, I'll show the calculation real quick. Okay, so for example, I have a mu of 50 and a standard deviation of 10, and then I have a sample that I collected of 51. Now the question is 51 different enough from 50? With a standard deviation of 10, that's going to be rough, right? Because I only have a one unit difference here. But let's look at the difference between having a low sample and a high sample. When I plug in my low sample of 25 individuals, I get a standard error of 2, which translates to a z-score of 0.5. So what does that mean? Think about it for a second in terms of what that z-score is. Z-score of 0.5 is not larger than 1.96, so I fail to reject. Now let's look at a sample size of 400. Plug in those same exact numbers, but I'm taking the square root of 400, which is 20. Then I plug that into my z-score calculation, and I get 2. So with those exact same numbers, nothing changes but my sample size. I can go from not significant to statistically significant just from changing my sample size. So keep that in mind. Variability affects the statistical significance, and so does the sample size. So last slide, some basic necessary assumptions for hypothesis testing. It needs to be a random sample, so randomly sampled from the population. Each person has to have equal opportunity to be selected. Independent observations. I can't go and recruit Stacy, who then told Nicole, who then told Diane that there's a study, because they're not independent observers anymore. They're dependent. So just like when you guys did the marble experiment in class, you randomly went and you grabbed 4 marbles out. You didn't look and pick out which ones you wanted. So it needs to be independent observations. Also, we assume that the standard deviation remains unchanged by treatment. So variability is not affected, only the average is affected. And then lastly, we assume a normal distribution, normal sampling distribution. And again, this comes with large samples. Ideally, we won't have large samples. And so to demonstrate that idea right here of the standard deviation being unchanged, only my average shifts, the standard deviation remains as is, right? My variability remains the same, so I simply just shift. Basketball players are bigger than or taller than the average woman. Okay, and I think, what slide am I on right now? 28. Okay, perfect. I think that's where I'm going to stop. So in order to, let me just jump back here. For the rest of Chapter 8, I actually have a recording already uploaded, which is Hypothesis Testing, Effect Size, and Power. So if you want to watch that to finish the chapter, but that was slide 1 through 28 for Chapter 8, okay? All right, thanks guys. I'll see you later. Bye.